Okay, so thank you very much for letting me talk in the conference. It's always a great pleasure and a great honor because, you know, the more time goes by, the more participants are there. So there is a big competition. So what I want to discuss today is a work in progress. I'm not sure if it's even going to materialize to something publishable. I thought still it's interesting. So it's a fundamental group of a Riemann surface from what I call the Riemann existence theorem. Okay, so first let's discuss the motivation, because we all know that the fundamental group of a Riemann surface looks like this, right? This is what we all learn in complex analysis for third year. So if X is a Riemann surface, then the fundamental group of X is given by two G generators, which is subject to one relation. Okay, AI BI is basically the usual commutator relations, and they all show us this beautiful 2G GONS, which is a starting point for any analysis on the model of Riemann surfaces. So why am I interested in that, right? Because why do I care? Because usually when we think about algebraic curves, we think about equations, and we think in terms of cuts and analytic continuation. And of course, you have the picture to show you, but I never seen like a hard formal proof, at least in the literature, that I can start with pictures and I can end up in an effective way with, with this AI BI. So yes, you can find the intersection and you can do that, but the moment that the genus grows, it's becoming more and more challenging to do. And for a large swath of Riemann surfaces, you just don't have the, well-defined homology basis. Okay. So how do you get from the cuts and analytic continuation to the theorem above? So of course we show this through topological arguments usually, but I'm looking for a more direct proof. And you will see, towards the end of the lecture, you will see exactly what I mean. Now, if any of you knows a paper where what I'm about to tell you is already outlined, I would love you to point this to me. So basically, there is a great proverb that might be widely known in narrow circles. Unfortunately, I don't belong to those narrow circles, so I don't know about that. And this was something that made me curious as of 30 years ago when I actually completed my PhD. Okay. So let's start with an equation with complex numbers, f of xy, which is 0. It is very well known that every x has n roots counting multiplicity. And we know that and if xy is a rational function or a polynomial, there is a finite number of points, lambda 1 to lambda r, which belongs to CP1, where we have less points on the fiber, we just count the points, right? And lambda 1 and lambda r are the ramification points. Now, for each ramification point, we have lambda I, we have the preimages. Lambda 1 to psi1 to lambda 1 to psk. So lambda 1 lies on the sphere. Lambda 1 is here, the x coordinate. And for each lambda 1, I have less solutions than the n solutions if I don't count the multiplicities. Now, let's assume that the y preimages are psi1 to psk. Okay? Each preimage is given locally by the mapping z goes to z to the power of j, where j is basically the multiplicity of the mapping locally. And the sigma j equals n. Now, let's take a simplest example possible. Let's look on y squared equals x minus lambda y. I go from 1 to r. R usually is even. In this case, the ramification points are lambda I, because if I have some x which is not lambda I, x minus lambda I is going to be non-zero, and then I have two square roots here, y plus for y and minus y for a complex number. However, if x equals lambda I have only one square root, which is 0. So in this case, the ramification points are lambda I, and I have a local coordinate which is given by t equals square root of x minus lambda I, or x equals t squared plus lambda I. Now, one important point here, which I kind of omitted as infinity, but in infinity, instead of x, I just take 1 minus x. And I guess there's one square root of x, and this is going to be my local coordinate. So in this case, right, the mapping is actually 2 to 1. So even though you have only 1 point, you see the ramification in the local coordinate. And when people actually do analysis for serious analysis with algebraic curves, let's say hyperelliptic curves, in the classical era, they all start by looking on this local coordinate. So this is not a hoax. These people actually can use it. Okay. Now, for a general equation, I assume that we all know what analytic continuation is. The analytic continuation isn't as easy as it looks. So how do I encode analytic continuation? I encode the analytic continuation by picking a base point P on CP1, which has exactly n preimages. So I avoid the branch points. In this case, let's say here, I would pick any x which is not equal to lambda I. And this is going to be my base point on the CP1, which is a sphere. It has exactly n preimages. Now you create a loop surrounding the branch points and analytically continue across it. And then for the base point, you select a preimage Bj and lift sigma I. So sigma I is going to be a loop around one of these branch points. So we have R branch points. So we have sigma I's. And when you lift it, right, you start with the image Bj, you will end up in some other preimage of B, and this will impose a permutation representation on the set of this fiber above the base point. So the loop sigma I will end up on another image B of Bk, and this induces a permutation representation for each sigma I. And this permutation representation of sigma I is actually encodes the analytic continuation. So these are the loops. Now, if you compare it with the usual cuts, when I talk about cuts, I take my base point and I just draw a line directly into the branch point. But here it's a little bit more subtle. You don't go directly to the branch points. You kind of surround it, and you go back to P. And this, I think, is a little bit better because, when you have this kind of presentation of analytic continuation, you can actually rely on the fundamental group theory of coverings. So, it's much easier to handle fundamental groups and all these commutation relations if you think about analytic continuation in these terms and not just take this line and bang, put it into the branch points like they do usually in complex analysis courses. Now, anybody who teaches Riemann surface course shows the students of pictures of sheets coming together. But what is less known is that if you look on the pictures carefully, you can read the permutation representation from it. And how do you do that? The permutation can be broken into this joint union of cycles, and this is what we see in the picture. So here's an example of that. And this is not the hyperelliptic curve, right? So here's your base point B, and you have 4 sheets, B1, B2, B3, and B4. And you have 2 branch points here. And I cannot emphasize enough that this is not the branch picture of an elliptic curve, because all of these sheets will come together at those branch points. So in some sense, it's the simplest case. Here you see that I order the sheets, right? And then I have sigma 1, which when I go around this B1, you can see the picture that the first and the second sheets are coming together, and 3 and 4 are not coming together. So this sigma 1 is going to correspond to the cycle or to the permutation, which is defined by 1, 2, 3, 4. Now, how do you actually read it from the picture? It's actually very easy. You have this ordering, and you see that B1 and B2 are coming together, and this is what your 1, 2. And you see that 3 and 4 are not ramified, so it's going to be 3, 4. And in this case, if you look to sigma 2, this is a red dots, right? So if the first sheet and the third sheets are coming together, so it's going to be 1 through 1, 3. And then in this case, 2 and 4 are not coming together, right? So they are unramified. So then you have 2 and 4, and here you can actually have you basically break your sigma I into disjoint cycles. You know, and this theorem actually what enables you to kind of actually develop an analytical approach for Riemann surfaces as we see. And this is what we call I call a 3-4 curve. Doesn't matter why, because but it's like an example of this. Okay, so once again, this is kind of a more generic example of what is going on when you actually think about pictures and trying to connect them to sigma i's. Now, when you actually draw this, right, you don't put those, you don't name the sheets, you just do the, the sheets without giving them an order. And if you don't give them an order, you will not be able to read this, right? So this is kind of a this is kind of a picture with a labeling, if you want. And in my opinion, this is the correct way to show it to students. Okay. Now, so I can, so what I did basically, I actually assigned if you have fxy, I kind of assigned a permutation representation to it. The converse is also true. It turns out that the converse is also true, and you can encode algebraic curves via the permutation representation. And we have the following theorem. So let's let H1 to HR be permutation in a Sn satisfying the following two properties. The first property is that the product equals to 1, and the second property is that HI acts transitively on the set 1 to n. So there exists a compact algebraic curve X and a mapping from F to X to CP1 such that the permutation representation associated with X is precisely HI. This is a well-known stuff. This is not something that, I invented. I'm going to show precisely where the new stuff comes in. Okay, now how do you prove the theorem? And it's a sketch, and excuse me for the typos. So if you take the branch points, lambda 1 to lambda r, you look on the cover X minus F, these branch points. So this is the topological cover of the Riemann sphere minus lambda 1 to lambda r. Once again, I actually start with a compact version, okay? Because if it's non-compact version, you forget the point in infinity, and this is bad. You want to actually consider the point in infinity as an equal partner with other finite branch points. So you have the topological cover. Now, what is pi 1 of CP1 minus this? It's basically a free group on our generators subject to one relation. Now, where the generators are coming from? Well, they're coming from this picture. And why the product is 1? Well, you just kind of wrap it up from the other side of the sphere. So that's why this is true. Now, the permutation representation that I defined here corresponds to a cover of pi 1 minus this. And this is basically classical topological cover theory 101. Call this cover X op. So this is X open. This is without the branch points. So how you obtain X? To obtain X, we need to use a cycle decomposition of HI to compactify X op. More specifically, if lambda I is a branch point, then you use a cycle decomposition HI to find the number of preimages of HI. And for each preimage point, the local mapping will be X goes to X to the power of Ri, where Ri is the length of cycle corresponding to this preimage. So if you have a permutation representation, which is associated with sigma 1, the beautiful fact is that you can decompose it into cycles, into disjoint cycles, okay, which is coming from a pure theorem in the symmetric group. Now, each cycle will correspond to a branch point. The number of cycles will correspond to this branch to the number of branch points without counting multiplicity. And this R, right, will be just the length of the cycle. Okay? Now, this is probably classical construction. Lo and behold, I haven't seen this part anywhere. I mean, it's why it's probably a classical stuff, but you know, it's actually important to say it, and I'm saying it right now. No, okay. So here, so what you see here, you have this, you have this cross here of two sheets, and you can see that I'm like putting, I'm filling it with a disk in downstairs. I'm feeling like with a double copy of a disk upstairs, right? And this kind of double copy serves a bridge between, between the first and the second sheet, right? So this is exactly the classical Riemann, the classical Riemann surface theory that you see all the time. All I did here, right, is kind of tying explicitly to this permutation representation. And you can see that your local coordinate here will be basically x, and well, now the notation is abusive, right? But here you have a disk and it maps 2 to 1. So these two disks will map 2 to 1 to the disk on the sphere. Okay? Now, what is important here to understand that I characterized the surface, right, as an open surface plus filling the disks. So I want the fundamental group of the open surface, of the closed surface, not the open surface. That's important to understand. Okay? And what do we need to do that? We need the Van Kampen theorem as basically stated in Hatcher, page 30. Okay? So basically the theorem says the following. If you translate Hatcher to this setup, when you fill in the disks with a mapping x goes to x to the Ri, you basically have the following theorem. That you assume that Hi equals to the decomposition of cycles, where Ci are permutation cycles, each one has length Li. Then if pi 1 x op is a fundamental group of the topological cover of the open topological cover, the closed topological cover, you take this x op and you divide by n. And what is the n? N is a subgroup of pi x1 op, which is generated by the torsion. So it's generated by sigma I to the power of Li, if sigma I to the power of L belongs to the fundamental group. And we're going to talk in a moment how I find this fundamental group. And if it's not, then you can use delta, which is a permutation, to bring it in, right? And then you basically kill the element by delta. Now, how do you think about the theorem in a more kind of a wordy thing, right? Basically, those sigma i's to the power of Lj are torsion. So you take your x op and you just divide by the torsion and you're done. So pi 1 of x is now kind of torsion free. Okay? Once again, probably it is known. I'm not saying that I'm discovering the moon here, but I haven't seen this anywhere. This kind of formulation. And this is everything is purely classical. Here, this is not too much of originality. Okay. Now, so from the previous theorem, we get pi 1 of x. We need to first find the pi 1 of x op. So when I talk about pi 1 of x, I actually want to see the commutation relation. That's the problem that I'm posed. So this is not enough for me, because this is good to do abstract algebraic stuff. But if you want to do a really hardcore analysis on modeling of Riemann surfaces, you need to find, you need to get explicit generators here. And you will see that getting explicit generators is pretty easy. What is more challenging is to get the commutation relation. And that's what we're going to talk about towards the end of the talk. Okay? So first of all, how do I get pi 1 x op? So pi 1 of x op is associated with a permutation representation of the open surface, which is induced by H1 to HR. So you have basically the action of the fundamental group of the sphere minus R points on this permutation on this set of Sn, right? This is where the permutation representation is coming from, and the fundamental topology tells us that the fundamental group of the open surface is just a stabilizer of 1 or any other number in this permutation representation. Any other number will go as well because we have transitivity. So all these groups can conjugate to each other. So you can of course divide, you can of course define this group only up to conjugation unless it's normal inside the pi 1 of x. But if it's not normal, then you need to do conjugation. And that's where this will come in. Because it might be that sigma I to the power of Lj preserves some other number. It doesn't preserve 1 if it's not in the cycle decomposition of sigma I, but then it's not a problem. You will just find delta that will bring it back to pi 1 of x op, and you will kill pi 1 of x op with this, with this element. Okay, so pi 1 of x op is a stabilizer of 1 in this permutation representation. Now I want to get the generators of pi 1 of x op, and the generators of pi 1 of x op is actually probably easy to get, because in combinatorial group series there is a standard process of getting the generators of pi 1 of x op, which is a subgroup of pi 1 minus this lambda 1 to lambda r. So this is called the Schreier process. Now you will see countless books telling you, oh my God, how do we get homology bases, with all the pictures, yada 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 yada. You don't need any pictures. You basically have a very well-defined process how to get generators for this group. So you choose a representative with a minimal word length for 1 to n, okay, using the coset representation of the permutation representation. So here you need like an intuitive notion of word length, but because you have only one relation of the fundamental group of this guy, it's kind of clear that this is kind of true. And call this representative G1 to Gn, and then you basically take this Gk, you multiply by the generator, sigma I of the fundamental group, and then you just return with another coset representative, and you are done. This is a generator of pi 1 of x op. And not only that, every word in pi 1 of x op, you have a very well-defined process how to write this through these generators. Okay, so it's actually a very straightforward process. Pity that it's not being taught too often. So then you obtain pi 1x, you need to mod by n and rewrite one torsion relation through a commutator expression. So I'm going now to do this, right, explicitly for the hyperelliptic case. So you will see how I'm getting my commutation relation from this kind of seemingly abstract representation. So rather than to burden you with more stuff, let me show you how this works in the hyperelliptic case. And lo and behold, I didn't see this development anywhere, even for hyperelliptic. Usually when you look on a book for Farkas and Kra, they will draw you the fundamental homology basis. Now you also have this Stretov algorithm that is programmed into Maple, which I don't know how reliable it is, but let's assume it's reliable. But once again, it's an ad hoc process, and you want to actually get a process which will give you homology basis for large classes of Riemann surfaces, because that's the only way for you to do some modular relations there. Okay, so the simplest case is hyperelliptic case. The representation is all of them are just 1, 2. So you have two sheets coming together, and when you look on sigma I, when you go around the points, it goes from the first sheet to the second sheet. Very simple. However, this forces a number of branch points to be even, because otherwise you will not see the relations that I goes from 1 to R, 1, 2 equals 1. You have to have this relation. And this is the advantage of working with a sphere versus a affine space, Because if you have an affine space, you always need to worry about the point in infinity. Well, guess what? Here I'm not worrying about the point in infinity. I'm treating them all equal, at least from the homology basis view. Okay? Now, for this permutation representation, according to our recipe here, we need two representatives. Okay? For the cosets that represent 1 and the cosets that represent 2. So for the coset that represent 1, I choose a trivial element E, and for 2, we choose sigma 1. So if you look on all, you didn't need to choose sigma 1. You could also choose sigma 2 or sigma 5. It doesn't matter. What is happening here, and you can see it from the picture, that if you go around any branch point, it will actually change the sheets. It will go from the first to the second, because if it doesn't, then you have triviality, and then basically it means that that you can throw away this point. Okay, so all sigma I permutes the sheets except the trivial generator, which takes the first sheet and just leaves it intact. Okay, so I have two representatives. I have the element E, and I have sigma 1. Now watch the magic. Now we need to apply the Schreier process. So what we do first, we apply the sigma I to the trivial coset. Now, because sigma 1 is a representative, we are going to throw it. We're not going to use it. We're going to use the other ones. And in this case, the generator is going to be sigma I to sigma 1 inverse. Because sigma I will move to the same coset, so I will apply sigma 1 inverse to get back to the stabilizer. And the second one is basically I will apply sigma I on sigma 1, and sigma 1 sigma I is inside the stabilizer, so I'm not doing anything. So concludes that the generator of pi 1 of x open, when x is a hyperelliptic, has two types. Sigma 1 sigma I is type 1, and sigma I sigma 1 inverse is type 2. Here I'm not applying any relations. This is basically pure combinatorial group theory, Schreier process, nothing else. Now, so let's say if you have 6 ramification points, the open surface has the following collection of generators: sigma 1 square, sigma 1, sigma 2, sigma 1, sigma 3, sigma 1, sigma 4, sigma 1, sigma 5, and sigma 1, sigma 6. And sigma I, sigma 1 inverse, but it goes from 2 to 6 because sigma 1, if you take sigma 1 to sigma 1 inverse, it goes away. So it's boring, right? So this is 6 ramification points, and you have 11 generators, which is exactly what you would expect. So you have 1, 2, 3, 4, 5, 6 here, and you have 5 here, 6 plus 5. Last time I checked is 11. Okay? Now, for the case of hyperelliptic curves, sigma I square stabilizes 1. So we can apply this relationship directly without worrying about the conjugation directly to the set of generators. So here, right, I have sigma 1 square. Well, I know that it's trivial, so I will just remove it. Right? So sigma 1 square is trivial as it belongs to type 2 generators. How do I apply to sigma I square? Very easy. I have a relation sigma I square, it belongs to the generator. I present it directly through my generators. When I do it through my generators, I see that sigma I square is 1, right? So here I have that basically sigma I, sigma 1 inverse, sigma 1, sigma I, right, are basically inverse to each other. Now, sigma 1 equals to sigma 1 inverse, so I have the sigma I, sigma 1, and sigma 1, sigma I are equal to each other. So concludes the sigma I, sigma Y inverse is the inverse of sigma 1 to sigma I. So in this case, here, all the type 2 generators are gunners, and this generator is a gunner. And what we're left in the genus sig in the ramification point case, sigma 1, sigma 2, sigma 1, sigma 3, sigma 1, sigma 4, sigma 1, sigma 5, and sigma 5, sigma 6. Very easy, very simple, straightforward, completely straightforward. If I don't have this relation, right, I cannot say that this generator inverse to this generator, because sigma y, because you see I get like sigma y, sigma 2 or something like that. I'm not getting, right? I'm not getting the inverse. So the fact that sigma I square is 1 is actually very crucial. So the theorem is that the generator of pi 1x are of the form sigma y, sigma I is not equal to 1. So now we have the following generator for r equals 6 case. Sigma 1, sigma 2, sigma 1, sigma 3, sigma 1, sigma 4, sigma 1, sigma 5, and sigma 1 to sigma 6. So the last step is to observe how we can write the commutator relationship for the generator above. We use the fact, so first of all, we use the fact that the product of sigma I equals 1, and hence the last one, sigma 1 to sigma r, is redundant. But further, we have also relationship sigma r square through the generator sigma 1 to sigma I. Let us denote these generators by SI, and then we write this, so we write sigma r square as I go from r minus 1 to 1, r goes from r minus 1 to 1. Okay, what is this sigma I? It is basically, I'm using the relation inside the sphere, right? That sigma 1 to sigma 2 to sigma r equals 1. So I just take sigma r, I rewrite it through sigma I, and I'm just writing sigma r square as a combination of these guys inside the fundamental group of the sphere. Now, this is inside the stabilizer. So I'm now going to write it with sigma I, sigma 1 to sigma I go from 1 to r minus 1. And now I get this expression. Now, how do I get this expression? Well, here's an example. So if I want to find sigma 6 square, it's going to be sigma 5, sigma 4, sigma 3, sigma 2. Now it's going to be sigma 1, sigma 1, sigma 1, sigma 5, and sigma 4, sigma 3. So sigma 5, sigma 4, sigma 3, sigma 2, and sigma 1, sigma 5, sigma 4, sigma 3, and at the end I also have sigma 2, sigma 1. So I'm taking this guy and I'm just rewriting it twice. When I'm using the Nielsen-Schreier, I have sigma 5, sigma 1, sigma 1, sigma 4. I insert. If I have a generator, I'm not doing it anything. But if I have something like sigma 3, sigma 2, I'm just inserting the sigma 1 or sigma 1 inverse sigma 1, sigma 2 here. You see how it goes? So I have a generator of the form sigma 3, sigma 1. Here I have sigma 1, sigma 3. They're inverse to each other, and that's how I'm getting this expression. And now comes the coup de grace. Yaacov, how you take this expression, you turn it into a commutation relation. Well, that's the end of the story. How to write expression of the form as commutation relation? We need to use the fact that xy, right, equals to xy, yx inverse. So you have xy equals xy times yx. And now, in this case, for example, consider x, which is equals to this, and y, which is equals to this. Now, you can see what I'm trying to do here. If you look on this expression, I'm taking this guy here, SR minus 1 to SR2 minus 1, and I'm moving it to here in the middle. So I'm taking this element and I'm changing it with this element. That's the secret, ladies and gentlemen. That's all. So I get my commutation relations, and as a byproduct, I'm also getting the standardized homology basis expressed through these generators. And for the hyperelliptic curve, doesn't matter. It's actually easier. Is it as easy to that in other cases? No. But the process goes, works exactly the same. You basically start modifying your generators, right? So that you get your commutation relation. Is it finally proved? No, but I played with it, so I'm pretty sure that it actually works. So I've outlined how to get the fundamental group of the closed Riemann surface, and commutation relation should follow in a similar way like in the hyperelliptic case. So you have this redundant relation with sigma r, and this is where it is important to sigma r, because if you wouldn't see the sigma r, you wouldn't be able to get the commutation relations, guaranteed. Okay? So only in the compact version it works. For me, it was a great surprise. You just tuck, do the picture, it should follow. No, you still need to have a work to do. and you have this following commutation relations, these are your generators. These are your 2G generators. And you can see how beautifully recursively it is done. And I don't know if you can see this picture if you look on Farkas and Kra Riemann surface, because you have these pictures there. Okay. The general case is harder, but I think it should work the same. I mean, still need to do the math. And I'm coming to an age where I have no energy to do the math. So maybe it's classical, but the lack of a simple method to generate commutation relation is an obstacle to study model space of algebraic curves. Any questions? I'm done. Any questions?
Yaacov, may I ask you? The question is, can you clarify once again? You say that you consider CP1. This is topologically just a sphere. Then you throw out several points, and you claim that the fundamental group is a free quotient by some relation. Or
no. I'm not claiming that. What I'm claiming is, right, that if you have a Riemann surface, you throw the branch points downstairs and upstairs, you get an open surface of CP1 minus branch points, right? This is going to be a subgroup of the fundamental group of the sphere. And when you take this subgroup of the fundamental group of the sphere and you mod by the torsion, you get the fundamental relation of the algebraic curve. You get the fundamental group of the algebraic curve.
So I understand. So because if you have an open surface, that is, its fundamental group is always free.
Yeah, I know, but I'm actually putting the disks back in. That's the whole point.
I understand. No, yes, I understand. Thank you. And maybe another remark that we will have on Thursday on the morning. We will have two talks devoted to computation of the fundamental group of algebraic surfaces. So this is very close, and one of the talks will be given by Meirav Topol. I think she's presented here. So I saw that your talk and Meirav talk are very close, but I cannot put them together. It's the same because due to time zones. So if you'll have a possibility, would Meirav maybe say something? Yes, Meirav, please say. Well, no. So I just want to mention that there will be some talks which related to the same to the computation of the fundamental group. So and I saw that Meirav. Yes, please say.
Yes.
But Meirav considers much more challenging problem.
Yaacov, it was amazing talk. Thank you. I enjoyed very much. Really amazing. Yes, I come from the direction of if I want to classify algebraic surfaces, I can come from two directions. One can be just plane curve, okay, a plane curve, or I can also classify surfaces through branch curves. We can use more or less the same techniques, the same tools, but there are also some differences. So you can see it on Thursday. I will show you some nice techniques. But this work of Yaacov is very, very nice. I love the talk very much.
Thank you, Meirav. Yeah, I mean, one of the sources of the inspiration of the talk was the discussion that we had last year.
Yeah. So in my talk in the beginning, you will see more or less the introduction will be the same, but then later on some development of how I deal with the much complicated cases.
Yeah, absolutely. And I think I'm not sure. Here, right? The whole point is compactification. And I think that in your case, you still look on the open case. So I haven't seen in your work that you actually put the divisors back in and you try to kind of kill the torsion. And I think if you do that, and this is just an idea, I think you will get a much simpler groups. That's kind of what I think, but maybe I'm wrong because, I'm not Moshe Zon.
Yeah, in one of the groups we used some similar nice thing that you did with the commutators. Yeah, but wow, I must admit that what you do is not easy. It's not easy at all to do these computations. I don't know why you say that it's
because it's not publishable, Mirav, that's why.
You think
in
so?
this
I
day
think
and age,
it's
it will not be
great. I think
publishable,
it's
but
a
that's a
great
different
work.
discussion.
I think it's a great work. I think you can publish it very easily. It's a very
we
nice.
We can discuss
work.
it. We can discuss it. We can discuss it separately. But I know exactly what you're doing because I know exactly what you're doing because I made some computations of the modular action of this kind of braid groups on this homology basis when I was younger. So I know exactly how it works in your case, and in your case it is much more challenging because you don't have Van Kampen. Here I have Van Kampen. There you don't have Van Kampen. So it's a much more complicated business proposition in your case.
So if I just want to classify plane curves, for example, to try to find some potential Ritz keepers, then I can use Van Kampen. If I come from the direction of surfaces and I use some degeneration, then it's a bit indirect way. Yes, but in some cases I do use some Van Kampen theorem. But there are a few versions there. There are a few versions. I use the simple one. If I see a node, then it's a commutation. If I see a branch point, it's equation, it's equality, and so on. Yes.
Yeah.
Because we proved already all the relations. It's not a. I know if I see something, then I know exactly which relation to take already.
I see.
Also, the degeneration gives us complicated singularities. Yeah. Also, for example, in plane curves to find the Ritz keepers, we have also some complicated singularities. Yes, it's challenging.
I can anticipate that it's very challenging. This is the easy case, But very good. Thank you very much.
It's the easy case, and it looks very, very challenging already in the easy case. So I don't know. Yeah, thank you, Yaacov. I enjoyed very much, really.
Okay, any other questions?
I would like to ask you about the following. Please answer me. You consider it in some aspect elliptic functions, elliptic curves, something about.
Well, of course. I mean, if you look, I'm doing this, right? Because I want to actually, one of the motivations, right, is to kind of generalize whatever you do with elliptic curves and elliptic functions to the higher dimensional case. Now, there is already a generalization which was done by Julia and Dmitry and Victor and the late Victor Yanolsky, right?
Yes, but I would like to consider the following part of my question. It's connected with Calabi-Yau manifold, maybe, and they are determined through Weierstrass forms, which are also connected with elliptic functions. Maybe you can say something about it.
I'm not sure I can, because, you know, unless I want to give you like a jerk-knee reaction, right? Because I don't know Calabi-Yau. I mean, the only things that I know about this,
But-
that it's, you know,
Mhm.
I
But
don't
there
know. I
are-
mean, of course I know Weierstrass points, but it's not clear to me how these computations are actually related to Calabi-Yau manifolds.
But you said about modular forms, and I know that Calabi-Yau connected with possibility of conformal transformations, which are connected with possibility of modular forms.
Okay, I see what
consideration.
you're saying. Okay, so basically,
Mhm.
when you have a homology basis here, right? If you look on these points here, if you look on the branch points, okay, here, lambda 1 to lambda r, you're asking yourself, what happens if I'm going to change, you know, if I'm going to swap the branch points. And if you swap the branch points, it's basically your configuration space will be r points inside CP1, so it's going to be the projective space. Okay, so what you can do, you have the braid group which is acting here on all the shebang, and hence it's actually acting on all these Riemann surfaces. If you look on the hyperelliptic case, because all this all the permutations are 1, 2, you have the entire braid group which is going to act on this homology basis, okay? And then you are going to get some sort of Bureau representation of the braid group, which is mapping class group for hyperelliptic curves, right? Inside the symplectic group of 2G, where G is the genus of the surface. So, for example, you have a symplectic group in genus 2. You have a symplectic 4Z. Now, what you want to do, right? You want to classify genus 2 or higher genus hyperelliptic curves, just like you classify, okay, elliptic curves using the J invariant. Okay, and you can do it here.
Yes.
You can do it here using what we call Iguza invariance. And you can do it in general using the invariant theory, what they call invariant theory of binary forms. So you can actually classify hyperelliptic curves, okay? And you can classify these Bureau representations using, using this technique. So you can do it. You can actually, and this is the only case where it's actually can be done. If you are looking on other cases where it's not hyperelliptic, even cyclic covers, you don't have this kind of you don't have this kind of a theory to classify. But in hyperelliptic curves, you can classify hyperelliptic curves using invariance of binary forms, what they call Iguza invariance, but in reality it was Bolsa that did it all, and they just copy pasted him.
It
or
is more
some of it.
more complex space, and it's necessary more different invariants. Yes.
Yes, exactly. So for genus 2, I think we have 3 or 4 invariants. For higher genuses, if you have a hyperelliptic curve, you have 2G minus, I think 2G minus 1 or something like that invariance. Once you step out of the hyperelliptic case, you're like a blind bat. This is basically the major questions that was asked by Riemann, right? How do I actually classify curves? How do I give invariant for curves, just like I did with the elliptic case, which was well known in his case of the J invariant? And it's an open question. We don't know how to do it. Even if it's possible, we have no idea. But this kind of my computations are kind of dealing with a different problem. I'm kind of trying to see if for larger classes of moduli space, I can give this kind of homology basis. And once I have this homology basis, then I can do the things that we discussed now, like, for example, acting with a braid group and see what kind of result I get. But I can't do it before I'm getting a homology basis. That's a problem. because you need theta functions. Theta functions are working, or even sigma functions, you express them through the normalized periods, you know. So it's challenging, even though Dima Leikin kind of gave an alternative way to do it, which is unfortunately is not well known. It's a great work, by the way. Any questions? Sergey, thank you very much for inviting me to speak. It's always a pleasure.
Well, welcome. Thank you very much for coming just virtually, but I hope that maybe next year you can do
Next
this
year,
in person.
I'll be, the moment that Borispol is open, I'm going to be in Odessa eating your beautiful bычки.
Welcome, Yaacov.
Yeah, it's a great time. It's a great city.
Well-
Highly recommend it.
Well, so are there any questions, comments, remarks? Okay, if not, let us thank the speaker again. Yaacov, thank you very much. Very interesting talk. Very many people are interested in this topic.
I'm glad.
Well-
I'm glad. Thank you.